All right. So in this problem, we've got this block pressed against this horizontal spring. And I definitely see some ideas of the conservation of energy here. Because we can say in the block spring earth system, as the block goes from its compressed length to its extended length, this system is going to have spring potential energy, and that's going to turn into kinetic energy. What I'm assuming here is that there's no gravitational potential energy. I'm setting y equal to 0 right at that point. And that I'm only looking at the motion on the table. I can't use Newton's laws in one-dimensional motion here because the acceleration isn't constant as the spring extends. The spring constantly changes the force that is acting on the block. So that changes the acceleration, which means I can't use my kinematic equations. So energy is the way to go. Now, as I go forward with that, I can say that, okay, that's 1/2 k delta x initial squared equals 1/2 mass of the block times the speed of the block after it leaves the spring squared. For that one, problem is, I don't know how fast the block is going after it leaves the spring. So I need to pay attention to the projectile part of this problem. The fact that I know that this is 0.6 meters and that this is 0.8 meters. And I can say delta y, v initial, v final, a, and delta t. That's everything that's true vertically. And I can also look at what's happening horizontally and look at those unknowns, and I'm going to define positive and down is to the right, a totally separate problem than the energy part of the problem. I know the initial vertical velocity is 0, and I know the horizontal velocity is what I'm trying to find, so I know the acceleration is 9.8 meters per second squared downward, and we've got 0.6 meters of vertical displacement and 0.8 meters of horizontal displacement. Now, this is a great opportunity to use the kinematic equations and review our physics from the beginning of the year. If you're doing this correct, you're going to get a time of 0.35 seconds. And one note that the vertical velocity is 0 because the block is just launched horizontally. It doesn't have any vertical velocity in the beginning. And then this becomes 0.8 divided by 0.35. I got 2.28 or 2.3 meters per second of speed as it leaves the table. Then I can say, okay, I know the spring constant, I know delta x, I know the speed of this block, I can solve for the mass. I'll do that real quick in my calculator. So that's 0.5 times 600 newtons per meter times 0.05 squared times 2 to get rid of that 1/2 divided by 2.3 squared, and a mass of 0.28 kilograms. There's another great way to do this problem where instead of saying the final condition is after the block leaves the spring, some people set the final condition as down here, right before the block hits the table. And so they say spring potential energy equals kinetic energy at the end, and then there's also some gravitational potential energy if you define y equals 0 at the ground. If you solved it that way, that's a great way to look at this problem as well. Still totally works. You just need that total velocity of the block as it right before it hits the ground. So that's 2.3 meters per second. And then that's the horizontal velocity. The vertical velocity is 9.8 times 2 times 0.6. Square root of that. 3.4 meters per second. And what you need is this would be your total velocity that you'd plug in here. Either way, and that being the hypotenuse of those two velocities. So either way, you're going to get the mass of the block is 0.28 kilograms, and I like that there are lots of good ways to go about this problem. Make sure you feel good about them all. Thanks.